So we saw this idea of the hypothesis class, the model that represents the hypothesis class, and then we need to find the best hypothesis. So now I'll start the introduction to supervised learning with the problem of finding this best hypothesis in the context of supervised learning. So when we have labeled data and we can evaluate the performance of each hypothesis, comparing it to what we know the results should be. So in supervised learning, we're going to see these basic concepts again and how this works. We're going to look at the difference between regression and classification, and then we're going to look at the specific example of fitting a curve with least mean squared, with this squared error minimization as an example of finding that best hypothesis. So let's start with this basic idea, basic concept for supervised learning. Let's suppose that we have a set of labeled data where this X I'll be using to represent a vector of features. This can be a vector of numerical values describing some image or something like that, can be anything, but these are the features that we can typically observe in any example. And then we have this epsilon here, which represents the value we're trying to predict. This is something that typically we have in a specific set, our training set, but it's something that we are then going to predict for new examples. This can be the probability of someone developing some kind of disease, or which category an image belongs to, or what will be the price of a house after 5 years, something like that. And we're going to assume that there is some function somewhere in the universe, we don't know this function, but there is some function that allows us to predict this epsilon value from the X value. So it maps the features into the thing we want to predict. For instance, it maps a set of biochemical tests into a probability of having some disease or something like that. So there is this function, we don't know what that function is, but it maps the features onto whatever we want to predict. And now the goal of supervised learning is to find one function that we're going to make up. So this is a hypothesis from our hypothesis class that will receive as input the X values and also has some parameters that we can adjust in order to choose the best hypothesis. Note that we need to have a preconceived idea of what shape this function will have, because this is basically the hypothesis class. The hypothesis class will determine what functions we can use. And we want to find this function with the right parameters so that we can predict that epsilon from X. And we're going to use our set of labeled data to find those parameters, or even to find the function, because as we'll see later on, we can consider different hypothesis classes and then try to figure out which one is best for our problem. So we're going to try to approximate this F function here. This F is some unknown function, would be the oracle if we had one, and we're going to approximate it with G that has these parameters that we can adjust. And this is supervised learning because for any instance of these parameters, we can run our example through our function, see what the function is predicting, and compare that to all the epsilons we already know. So we can tell if it's improving or not and how well the performance is. So ideally, we want to approximate that F function not only for the data that we have, but for any possible data. It's not very interesting to have a system that can predict what we already know, but then fails horribly at whatever something new comes along. So in general, what we want is to improve performance for the new examples and not for the ones we already know. But for this lecture today, we're going to focus on only the training set. So we are adjusting our function to the data that we already know, and we are going to ignore the problem of adjusting it to new data points. So this training set is the set of labeled points that we have and that we can use to adjust our parameters to find the best hypothesis. The training error or empirical error, or as Mitchell calls it, the sample error, is the error we can measure on this set. So if we run all our data through one hypothesis, one instance of these set of parameters, we can get all the predictions from our function, from that hypothesis, and then compare that to all the values that we know. This way we can measure the error, and this is the training error, or empirical error, or sample error, because we are measuring the error on the data that we have. This doesn't tell us if it's going to make lots of mistakes outside the data that we have. But we are not going to worry about that for now. We'll start worrying about that next week. So our machine learning problem for today, we can specify it as trying to predict the values in our training set. This is not a very interesting problem because we already know these values, but at least we can specify it very clearly. We're going to use as a measure of performance the error between the data, the values that we know and the values our hypotheses are predicting, and the data that we have will be this abstract set where we have the features and the corresponding value we want to predict. This can be a classification problem if this epsilon is a category, say red, blue, or A, B, C, D, something like that. Then if it's discrete and we're trying to group things into the different categories, it's a classification problem. A regression problem is one in which epsilon is a continuous value that we want to predict, like a price or height or something like that. So we're going to look today at regression problems because it's easier to represent them graphically and to understand this problem. So let's see an example. We're going to do a linear regression. This is one where we have those coefficients multiplied by whatever features we have, and we sum everything up linearly. So we're going to do a polynomial fitting, and a polynomial is a curve, so intuitively it may not seem that we're doing a linear regression, but actually a polynomial regression is an example of a linear regression. And this will be why it is an example of a linear regression will be an important lesson for today, because we're going to see how something can be linear but still curved at the same time. So as an example, we'll start with the straight line before we complicate things. And so we have this class of hypotheses, which is the set of straight lines in 2 dimensions. We can describe that with a model. We have this epsilon equals to x multiplied by one parameter plus another parameter. So the first parameter tells us the inclination of the line, the other one where the line is placed. So with this model, we can, adjusting the parameters, describe any line in our hypothesis space. And now the goal will be to find the best line that fits our data. So the line that better allows us to predict the epsilon values for our data. So the problem now is we have this data set. These are our data points, the red dots there. And we want to know which one is the best line. What is the criteria that we're going to use to decide that one line is better than another? Let's assume that we have in our data the epsilon value is a function of the x value. This function f, we don't know what it is, plus some noise, because there may be random errors in our sampling, in our measurements, something that's happening. But basically the idea is that for each of these points, the epsilon value here is determined by the x value, applies some function, we don't know what it is, and then there is some error because of whatever is happening. So this is the general idea. Each epsilon comes from this function applied to x plus some error, and we're going to try to approximate x with our g function, which is that straight line. We have those 2 theta parameters. Those are the parameters we can move, and we're going to try to approximate to find the parameters that make g as close to s as possible. And we're going to assume that this error here, note one thing, we are assuming that the error only applies to epsilon, not to x. This sometimes is true because sometimes we can measure some feature very well and then in the data there is some noise. Sometimes it's not true, but remember that we always have this kind of bias. So you need to be aware of what you're assuming when you're trying to figure out how to solve the problem. And we're also going to assume that this error has a normal distribution around the correct value. So the error is centered on 0, maybe positive or negative, and it has a normal distribution with some variance, standard deviation sigma. We don't know which one, what value it is, but it's normally distributed around 0. So some points will go above what fx is saying, some below, but most will be around fx because that's the big part of the distribution here. Now we have a set of data points, these points here in red. This is what we know. We know the x and we know the y for each of them. And we also know this is basic probability, that the probability of two values, the joint probability of them occurring together, is the probability of one conditioned on the other. So knowing that the other one has that value, we have the probability of this one having this value multiplied by the marginal probability of the other. But this is basically just a way of rewriting the expression. So we know that the probability of having this data set here, so this x with that y, this x with that y, basically all of these things here, is the product of the probability of each one of them individually, and this is the product of the probability of having each y given that it has that value x multiplied by the probability of having that value x. So if you multiply all these probabilities, we have the probability of our data set. Now what we want to do is to find the parameters for our function that can increase or maximize the probability of our data. This seems like a bit of a convoluted reasoning, but if you remember from probabilities, we say that random variable and the probability of occurring a certain value will be the frequency that value occurs when we repeat the randomness, the experiment, infinite number of times. So if we repeat things infinite number of times and the coin in that infinite number of throws falls 50% of the time heads, then the probability of falling heads is 50%. So this is something we can apply to random variables, to things that are different at each sample. And we are going to assume that the data we have is a random sample of all the possible data points. However, the parameters here, these set of values, are not random variables. They will not be different at random because we're trying to approximate that function, and the correct parameters should be exactly those values and not something that appears at random. So the parameters are not random variables. We cannot talk about the probability of the parameter being this or that. We can if we talk about Bayesian probabilities, and we'll cover a bit of that later on, but in a frequency sense, it doesn't make sense to talk about probabilities of something that is not random. So what we're talking about here is the likelihood. We want to find the parameters that maximize the probability of finding that distribution of points. And those should be the most correct parameters, the best parameters for our straight line. So we're going to find the parameters for G that maximize this product of probability. This would be the maximum likelihood parameter. So we're going to use this product here. We can take the logarithm of the likelihood because the value for our parameter theta that maximizes the likelihood is the same value that maximizes the logarithm of the likelihood. So we're going to try to find the maximum. We can do it in logarithms too. And when we do with logarithms, we can throw away the products and replace them with sums. And also, we can simplify this by ignoring the probability of x. Note that our function receives x, predicts y, and we want to adjust the parameters to maximize or minimize the error or maximize the performance in predicting y. The probability of x is irrelevant because we already have that data. What matters to us is the probability of having some y value given that x value. So this will be proportional to this part here, which is constant with respect to our parameters theta. This will never change. So we want to maximize the logarithm of this product, and we can replace this probability here of y given x by using our initial assumption that y is a function of x plus this normal error, and that x is approximated by our function g. So if we replace that here, this is the equation for the normal distribution, for the error, and here is our function g, which is the prediction for that value. So the probability of having a specific x having that y is somewhere distributed around the best function g that we can find with this normal distribution for the error. Since we have this logarithm here, we can simplify the expression, throw away the product and the exponent there, and we have this expression here. So basically, the logarithm of the likelihood of our parameters given this data set is proportional to the negative to minus the error, the quadratic error between the values and the prediction. So this is a bit of a complicated trajectory here, but what we get in the end, under this assumption that all the error is on the epsilon value, it's normally distributed, we get this conclusion that the likelihood of our parameter is proportional to the negative of the error. So if we want to maximize the likelihood of our parameters, we need to minimize this quadratic error. And basically this will be the criteria for finding the best hypothesis. The best line will be the one in which the sum of the quadratic error between what we know the value should be and what the line predicts is as small as possible. So in this case, the maximum likelihood prediction for our parameters corresponds to the minimum quadratic error, minimizing this quadratic error, which is often written in this way. So usually when you see these expressions for the quadratic error, you'll find this 1/2 term here. This makes no difference because we're looking at the minimum value. We want to find the parameters that minimize the expression. So dividing everything by 2 gives the same result. The minimum is the same. But when you compute the derivative, that 2 of the square there gets multiplied here, and then it cancels out and the expression becomes simpler. So this is usually what you're going to see for convenience. Actually, we're trying to minimize the quadratic error, but the important message here is why we're trying to minimize the quadratic error. Because we assumed the error was on the epsilon value, normally distributed, and when our function approaches that, then the likelihood of the parameters will, maximizing the likelihood of the parameters corresponds to minimizing the quadratic error. So this is basically what we need to do when we're trying to decide on the algorithms we use for solving machine learning problems. As you can see, it can be a bit complicated because depending on the kind of algorithms, this can be quite convoluted, and we're going to see some even more complex examples more later in the course. But once you have this solution, you know that if you find the minimum of this value, you know what you're going to get. You're going to get the parameters that maximize likelihood, assuming those assumptions we had at the beginning. So how are we going to do this? We're going to do this by least mean squares minimization. We're going to minimize the quadratic error to find the best line here. So each of these lines corresponds to a pair of theta parameters, theta 1 and theta 2. They give the inclination and the position of the line. And we can measure the quadratic error between the line and the point by measuring these distances. So at the same value of x, the line predicts this, the value should be this one. The point is actually here, so this is the error. We can square that and do that for all the points. So we can imagine doing that for every combination of inclination and the position of the line, and we could have something like this. So this would be, as we change the inclination and the position of the line, we can reduce or increase the quadratic error. Basically what we're doing is we're computing for all our data sets the difference between the predicted value and the actual value, measure everything, all these differences squared with sum, and then we plot that here on the chart. Now, what we need to do is find the minimum of that surface. We need to roll down the surface in order to find the combination of parameters that minimizes this total quadratic error. And this is what the optimization algorithm will do. We'll basically start with a random guess, compute the derivative there, and then follow along the derivative until it reaches a minimum. Then it computes the derivative of the error here, it follows along until it reaches a new minimum, and continues like that. So if the function is well behaved, and typically these sums of quadratic terms tend to be well behaved, after a few iterations it reaches very close to the minimum and we have a good solution. So this is how we proceed in order to find the best hypothesis. We need to know what our assumptions are, how to go from there in order to figure out what is a good hypothesis or a bad hypothesis. Then we reach something like this, some recipe like this, minimize this quadratic error, and now we use a numerical solver to minimize this quadratic error. In this course, we are not going to look at how the solver does it. We just use some minimization library and have the result. So this is the best hypothesis for our data, given this measure of performance. And as you can see, it's not a very good hypothesis because we are overestimating the value of the points here and underestimating there, and we are not fitting the data very well with this line. So we need to curve the line. We cannot fit that data with a straight line. And we are still going to do this linear regression all the same, but we cannot make a curve with a straight line. So what we're going to do is we're going to do a straight line or straight plane in 3 dimensions. And we're going to create a new data set which has the same epsilon values, the same x values as the original ones here in x2, but in x1 we're going to put the square of the original x value. So now we have a 3-dimensional data set that we computed from the first one, and we just added the square of the x value to the features. So now for each point we have 2 features. One is the original value, the other is that value squared. And this is the representation of our new data points. We still have this curve here, but now instead of it being on this plane, it is on this, like the surface of a barrel, this round surface here, because the 2 x values are the original x and the x squared. So we have this quadratic curve here, and we have all our data in this curved surface in 3 dimensions. So now we're going to do again a linear regression and find the best hypothesis, but from this different hypothesis class. The original one had only 2 parameters because it was a line in 2 dimensions. This one has 3 parameters because it's a plane in 3 dimensions. But it's still linear. It's still each parameter multiplied by one of the coordinates, and just sum everything and try to predict the epsilon. We do it the same way. We minimize the quadratic error for the same reasons. We are assuming the error on the epsilon, normally distributed error, and so forth. And we have this solution here. So this is the plane that best fits the points that we have when they are spread out in this curved surface in 3 dimensions. This is also a straight plane. Everything is straight there. But we are now adjusting this to the 3-dimensional representation of our original 2-dimensional data set. And now we can convert this back by using the same transformation. So basically we are intersecting the plane that we computed with this surface that we have, like the size of a barrel that we obtained when we created this new coordinate from the x squared. So this is x squared, this is this quadratic curve here that we can imagine as a surface here, and when we intersect that with the plane, or when we try to bring it back to the original representation, we have this quadratic curve here. So basically what we have is this fit of our line. Why? Because what we're doing here, given that this is the square of this one, x1 is x squared and x2 is just a copy of x, this is actually a 2nd-degree polynomial that we're trying to fit. So it looks like a straight plane in 3 dimensions, but in 2 dimensions it's a 2nd-degree polynomial when we intersect that with that curved surface. So we do the same thing. This is also a linear regression. We are doing it either, you can imagine it simply by doing it instead of a line, we're doing it with a 2nd-degree polynomial, but you can also conceptually imagine that we are not doing a curved line in 2 dimensions. We are working with a straight plane in 3 dimensions after transforming our data with a nonlinear transformation by using that square on one of the coordinates. And this is an important part because we're going to see this later on in classifiers and so on, where we are usually dealing with linear linear models. So our hypothesis class is about straight things, straight lines, straight planes, but we can still use that to create curves when we increase the dimension of our data with some nonlinear transformation. So this is one thing we can do. We can go to a second degree polynomial. Although we can do the same thing for any degree that we want. Of course, representing things in 4 dimensions is even more confusing than in 3, so I'm not going to show that, but I'll show you a bit of what you can do to fit polynomials. So this would be an example we're going to do next week also in the tutorial class, and it's just a first introduction to Python that we're going to use for the tutorial. So first we're going to use this NumPy, which is a numerical library which allows us to deal with vectors and matrices and things like that, and has functions, for instance, for loading a CSV file into a matrix if everything is numerical data, and simplifies a lot of this work. So when you want to use some external module in Python, you just write import the name of the module, and optionally you can give it a nickname. So if we don't want to write NumPy all the time, we can call it NP. This is a common nickname for NumPy. And also for plotting, we import PyPlot and call it PLT, so we don't have to write all that. Now we're going to load the data for our points. So these points here, the red points, we have this in a CSV file, and we're going to use this load text function from the NumPy module. We specify a semicolon to separate the two columns on the file, and it reads that into a matrix object. Note that since we call this NumPy module NP, we call the load text inside NumPy. So this is an object, and that function works as a method for the object. Now we separate the two parts of the matrix into X, Y, and this is a notation that tells us we want all the rows and the first column. In Python, indexes start at 0, and we want all the rows in the second column. This gives us a tuple with the two columns, and it distributes those into X and Y. This seems a bit confusing in this way. I could have done it in 2 lines, X equals this, Y equals that, but this is just to show the kind of things that, the shortcuts you can use in Python. So the idea in this course will not be for you to learn a lot of Python, but just for you to learn enough Python so that writing the code is not an obstacle to understanding how things are working. And the reason for choosing Python is because it's easier to use, and you can focus on understanding the algorithms and how they work. So now we use the polyfit function from NumPy, which does a polynomial fit with the X and the Y values, and we tell the degree that we want. So basically, this is what we have to do to load the data and fit it, a polynomial of any degree with these libraries. Now this part is just to do a plot. I create 100 points from 0, evenly distributed from 0 to the maximum value of X, so that I can do a smooth line with 100 points. Then I compute the value of the polynomial with these coefficients for that point. So this basically will plot this line here. This is 100 points all connected by straight lines, but it seems curved because there are lots of points there. And then I create a figure. I plot the original data with red circles, so this OR is a circle in red. Then I plot the line with a dash or a line for the polynomial, and then I save the image and so on. So there's no need to go into much detail here because this is obvious, setting the size of the X is the title, saving the image and closing the plot. So this is basically the kind of things that you can do. You're going to experiment with this on the first tutorial with the basics of Python, but this makes it easier to see the results and to play around with these different models and try to find out, to get a feeling for how these things work. And that's what we're going to do now. We have this for second degree. It's still not very good. It seems that our data curves a bit more than the second degree polynomial, but we can increase the curvedness of our hypothesis. And the important idea here is that we are using something that is straight, in some sense. It's a linear combination of the different parts, and this is that straight plane in 3 dimensions, but it becomes curved because of the way we transform the data. And we can do this for more dimensions. If we go to 4 dimensions by adding an x cubed, or 5 dimensions by adding x raised to the fourth power and so forth, we can increase the dimensionality of the transformed data, which is the same as increasing the degree of the polynomial here. So we're going to curve more. For instance, we can go to this model here with the third degree polynomial, and now we can fit the data much better because we can do this curve. But we can increase, we can use a 5 degree or 15th degree. This one fits the data a lot better because now we can really adjust to this point. But the problem here is now that we can see that the error of this polynomial is much less smaller than this one, for example, because this one is not able to reach those points. But if we have a degree of 15, we can really reach the point. However, this gets a bit suspicious here. Why would we predict that for this value of x, the y would have that value? This seems a bit strange. We have these points distributed in this way, and we are making these very strange predictions. So at this point, we can start to suspect that even though we can arbitrarily decrease the error to our training data by increasing the power of, or increasing the complexity of our model and the power to adjust to the data, at some point we may be adjusting to things that are not really part of the f function that we wanted to predict, but are part of the noise that's also there. So as we start to adjust our model to the noise, we may start losing the ability to predict points outside our data. So now if we extract a new point in this region, we would expect it to be somewhere here, because that's where the other points are, but our function is predicting that it will be there. And this may give us a very big error now. So this may not be a good idea to use a polynomial of degree 15 to adjust this data. If we overfit the data, if we adjust too much to our data, we are actually adjusting the error part and not the f function, and we are losing ability to predict outside the data. So this is what we're going to see next week, how we can prevent overfitting our data. So to sum up for this part, we saw two different parts of supervised learning, just regression and classification. Classification when we're trying to predict some discrete category, but we focused more on regression, on linear regression, and we saw that given some assumptions about the function we're trying to approximate and the error, we can deduce what would be the way to find the most likely parameter. And that corresponds to minimizing the quadratic error. So we also saw how we can minimize the quadratic error. So the basic idea is that we start at a point, we go along the derivatives until we reach the bottom, and we use that to fit a straight line. But we can also fit a straight plane or a straight hyperplane in n dimensions, and if we transform our data adequately in a non-linear fashion, these can correspond to curved lines in the original dimensional space. So this is actually what we do when we are doing polynomial regression. We are pretending, or we can conceivably think of that as going into higher dimensions, fitting the plane, and then coming back and to see how that plane intersects with the surface of our point. But this can be too much if we increase the flexibility of our models. So not all hypothesis classes are equally adequate for each data set. And this is what we're going to see next week. So these are some chapters that I recommend that you read about this part of the subject matter. And if you have questions, we have some time.